In this section, we're going to look at applied problems. We're going to look at the first derivative, the second derivative, and we're going to look at the first derivative test and the second derivative test to see how they apply to real-world situations. In real-world situations, often you're trying to find a max or min, and you're trying to find it in the shortest amount of time. In that case, we are going to use the second derivative test most often. What is the second derivative test? Well, if we already know that a number is a critical number, in other words, the derivative equals 0, and we know that the second derivative evaluated that number is positive, then we know the function has a local min. Why is that? Well, if the first derivative is 0, that's a critical number, so that could also be a max or min. If the second derivative is positive, I'll remind you of a relationship. If the second derivative is positive, that means the original function is concave up or happy. And if you already know that the first derivative equals a 0 out there, in other words, it's got a horizontal tangent line, then the only scenario is that it would be a local min. Likewise, if you have the second derivative and it's negative at that value, then the function has to be concave down. And if you know the first derivative equals 0, and remember the derivative is the tangent line, and if that tangent line slope is 0, then it has to be a max for you to be sad. So this is the second derivative test, and that's how we're going to use it in some real-world problems. Note that this test uses only the zeros. It is inconclusive if the second derivative equals 0, it's not positive or negative, or the second derivative does not exist. Okay, so it's only for the zeros, not the D and E. We know that this real-world situation involves bacteria. A lake is used for recreational swimming. It's treated periodically to control harmful bacteria growth. Suppose that T days, blah, blah, blah. We get our formula for the concentration of bacteria per cubic centimeter. How many days after treatment will the concentration be minimal? It's asking us to find a minimum. So in order to find max and mins, we're going to find the first derivative. So C prime of t is 60t minus 240. Now for our critical numbers, remember to do our second derivative test, we're only going to look at the zeros. Also, we don't care when it does not exist because this is a real world situation. I got t equals 4. Okay, so we need to check that this is a minimum, not a maximum. So second derivative test, we look at the second derivative of the function, and that is going to be 60, which is always positive. So in other words, here's what we have. The second derivative is positive always, which means the original function is concave up or happy. And if we already know at t equals 4, the first derivative is 0. That tells us the slope of that tangent line right there is 0, so we have a minimum. So how many days after treatment will the concentration be minimal? 4 days. That's the answer to the first question. Second question, what is the minimum concentration? So we need to find the concentration after 4 days. So C of 4, we plug that into the original equation. And that equals 20. And it's bacteria per cubic centimeter. So the smallest concentration of bacteria is after 4 days, and that smallest concentration is 20 bacteria per cubic centimeter. This real-world example involves botany. It says it is known from past experiments that the height in feet of a certain plant after a certain number of months is given approximately by this equation for 0 to 2 months. Then how long on average will it take a plant to reach its maximum height? What is the maximum height? So they're asking us to find a maximum. And so we need to find the derivative. So the derivative of h, we bring the constant down and bring the power exponent down. The new power is 1 less, so 1/2 minus 1 is negative 1/2. And the derivative of negative 2t is negative 2. And that will simplify to 2t to the negative 1/2 minus 2, which is the same as 2 over square root of t minus 2. So now we need to find the critical numbers. The critical numbers are only the zeros because we're not considering when it doesn't exist. So we get 2 over square root of t minus 2 equals 0. We get 2 over square root of t equals 2. Multiply by square root of t. So we get 2 equals 2 square root of t. Divide by 2, 1 equals square root of t. T has to be 1. So now we need to find the second derivative to see if this is a max or min. So the second derivative, we have our constant of 2. Bring down our exponent of negative 1/2. Our new exponent is negative 1/2 minus 1, so negative 3/2. And the derivative of 2 is 0. If I simplify this, I'm going to get negative 1 over, because the 2's cancel. Just like over here, this 4 cancels with this 2. And over t to the 3/2. So I need to evaluate the second derivative at 1. So it's going to be negative 1 over 1 to the 3/2, which equals negative 1, which is less than 0. In other words, it's negative. So here we have the chart for t equal 1. We know that the first derivative at 1 is 0. And we know the second derivative at 1 is negative. So that means the original function is concave down. And if the first derivative is 0, that means the tangent line is 0. So we have to have a max. So how long does it take on average for the plant to reach its maximum height? It would be 1. And our units are months, so 1 month to reach its maximum height. What is the maximum height? So we have to find h of 1. And h of 1 is 4 times 1 to the 1/2 minus 2 times 1. So that actually equals 2. And our units are feet. So calculus is really pretty nice because we're not going to have to graph it. This would be a weird graph and try to find values. We can just apply calculus really quickly to figure out that it reaches its maximum height after 1 month and its maximum height is 2 feet. For the next problem, we're going to look at some relationships. So I wanted to remind you of this slide from one of the last lessons. If you're wanting to know when your first derivative is increasing, you need to look at the second derivative and see when it's positive. Coinciding with that, the original function is concave up. But if you're wanting to figure out when your slope is increasing or when your slope has a maximum, in other words, right here, your slope is going to have a max because it goes from increasing to decreasing. So you go from increasing to decreasing, then you have a max at an inflection point. For this one, we're looking at politics. And in a newly incorporated city, the voting population in thousands is estimated to be n of t equals 30 plus 12t to the squared minus t cubed. And it's t is time in years from 0 to 8 years. When will the rate of growth be increasing? When will the rate of increase of n of t be most rapid? So if you're looking at n of t, and that's in thousands, so at time 0, the population that is voting is 30,000. So that kind of explains that. So, but the interesting thing is this asks, when will the rate of growth be increasing? Well, if you're talking about a rate, you're talking about the derivative. So we need to find out when n of t is increasing. So we're looking at a relationship. We're looking at, okay, when is n prime increasing? Well, that's when its derivative, which is n double prime, is positive, right? Whenever the derivative is positive, the function is increasing. But whenever the second derivative is positive, the original function is concave up. So we're looking for kind of a triple relationship here. So we need to find a derivative. So n prime of t equals 24t minus 3t squared. And since we need to look for when the second derivative is positive, we take the second derivative, and we get 24 minus 6t. So then we look at the critical numbers to figure out our intervals. And it's the zeros, so 24 minus 6t equals 0. So what is that? T equals 4. So our interval is in terms of 4. So we're going to make us a little chart here for t, time. And time starts at 0 here. So we're going to go from 0 to 4 and see what happens. And then we know something happens at 4. And then we're going to look from 4 to 8. That's where we're going to stop. And we're going to look at the second derivative. And what does that tell us about the first derivative? And what does that tell us about the original function? Okay, so we're going to figure something out here. So if I test the number in that first interval like 1, my second derivative is positive. I know at 4, my second derivative is a 0. If I test a number in the second interval, I get negative. So if the second derivative is positive, the first derivative is increasing. And the second derivative negative, the first derivative is decreasing. So what happens when you go from increasing to decreasing? You have a max. Now, let's look at the second derivative compared to the original. When the second derivative is positive, the original is concave up. When the second derivative is negative, the original is concave down. So what happens in between? An inflection point. And we had discussed in an earlier lecture that an inflection point is where you're either growing the fastest or decreasing the fastest. So our max occurs apparently at 4 years in. So when will the rate of growth be increasing? The first 4 years, you are increasing. Okay, so we're talking about these two, first 4 years. And when will the rate of increase be most rapid? It occurs a max at 4. So the first 4 years. And a max at 4 years. Now, what if it had said, what is the max? Then you would plug 4 back into the original equation, but it did not ask us that. So we're good.